Let's talk about solving logarithmic equations. So you can see here I have two different examples where I am solving for a variable that you are currently taking the logarithm of. So in these situations where you're trying to solve for that variable, there are typically three steps that we follow. So the first step is to isolate the logarithmic term on one side of your equation. And in order to do this, sometimes you might have multiple logs within the equation, and you might have to use your laws of logarithms to combine them into a single term or to a single log. We want to make sure it's isolated though. So whatever your logarithmic term is, it needs to be completely by itself. For example, I can see that taking the log of 2x, this is my logarithmic term that I want isolated. Right now, it's being multiplied by 3 and then adding 4, so I need to get that by itself. So the first thing I'm going to do to both sides is subtract 4. So we would have 3 times the log of 2x equals, if you take away 4, that's going to be 12. And then I want to divide this by 3 in order to get just the log by itself. So if I divide both sides by 3, we get the log of 2x equals 12 divided by 3 is 4. If I look at this example over here, the logarithm is already by itself, right? This is the natural log or log base e of the quantity 2 plus x equals 1. So both of these, we have finished step 1. Step 2, we are now going to utilize exponential form because our goal is to isolate this variable, which you're taking the logarithm of. We need to find a way to essentially get it out of a logarithm. And we know that our inverse function is an exponential function, so why not utilize that? So if we were to rewrite log base 10, remember that's a 10 there if it's not written, of 2x equals 4, we know this would be 10 to the 4th power equals 2x. And over here, the natural log is a log base e, so we would say e to the 1st power equals 2 plus x. Just in rewriting it with exponential form, we now have a variable that you're no longer taking the logarithm of. It's very easy to solve for that variable. So step 2, we've rewritten it in exponential form, and now we just need to solve for the variable. So 10 to the 4th, remember that is a 1 followed by 4 zeros, so that is 10,000 equals 2x. Dividing both sides by 2 will isolate x, so 10,000 divided by 2 would be 5,000. So our first answer would be 5,000. Over here, when we have a natural log, the natural log of 2 plus x equals 1. Remember, as soon as you have an e involved, we're probably going to have to use a calculator here. So in this case, when we rewrote it and we had e to the 1st power equals 2 plus x, I know I can isolate x by taking away 2, so that's going to be e minus 2, but I don't know what this is off the top of my head. So this is a situation where I'm going to use my calculator. So e is e to the 1st power. I'm just going to use that button there, e to the 1st, and then we were taking away 2, so minus 2. We're going to get about 0.7183 if we're rounding to 4 decimal places. So this is going to be an approximate answer. It's going to be about 0.7183. I'm going to do a couple of more examples just to show you some situations where it might start off a little bit more challenging. So for instance, this problem over here. Remember, your first step is to isolate the logarithmic term. But in this case, we have 2 logs, but they're both of the same base. So one way to handle this is to combine them using the laws of logarithms. So we are subtracting 2 logs of the same base. I know that that means we are really taking log base 2 of a quotient. And that quotient is x plus 1 divided by x minus 4. And then that equals 3. So now we have a single logarithm. It is isolated on the left side of the equation. So now we can go on to step 2 where we rewrite this as an exponential function. So in this case, we could say 2 cubed equals the quantity x plus 1 over the quantity x minus 4. 2 cubed we know is 8. So 8 equals x plus 1 over x minus 4. This is really a proportion, right? This is like saying 8 over 1. And we know to solve that, we could solve using cross products. So 8 times the quantity x minus 4 will equal the other cross product, 1 times x plus 1, or just x plus 1. So to solve this, we could say 8x minus 32 equals x plus 1. I would subtract x from both sides to get 7x over here, and I would add 32 to the other side to get 33, which means x equals 33 over 7. That would be our exact answer. If you wanted to divide it out and get 4 decimal places, like it asked, then we would get 4.7143. And there we go. The final type that I'd want to talk about is something where you actually have logarithms on both sides. So if that happens, that's okay. But in the end, you want to make sure that you have a single logarithm on one side equals a single logarithm on the other side. And ideally, and you'll see that here, these are both of the same base. So this is log base 10. This is also log base 10. So it's log base 10 of something equals log base 10 of something. And in that situation, once it's set up that way, you know that this has to equal this. So we need to get it so that we have a single logarithm isolated on both sides. So we want to first rewrite 2 times the logarithm of x. Remember, this is the same thing as log of x squared. So what's in this box is an x squared over here, equals over here log of 2 plus log of the quantity 3x plus or minus 4. Since you're adding 2 logarithms of the same base, this is the same as taking the logarithm of the product of 2 times 3x minus 4. So we have the log of x squared equals the log of, if I were to distribute the 2, it would be the quantity 6x minus 8. So 6x minus 8 is what's in this box over here. So a single logarithm equaling another logarithm, they both have the same base, then it follows that this quantity, x squared, should equal this quantity, 6x minus 8. So x squared equals 6x minus 8, and now we can solve for x. So if I take away 6x and add 8 so that this is set equal to 0, I know that this would factor to x minus 2 times x minus 4. So therefore, x would equal 2 and 4. You do want to check your answers to make sure that these work. When you're plugging something back in, you want to make sure that you're never able, remember, with a logarithm, we typically have it set up so that your domain, right, if you're doing log, base 2 of x, for instance, your domain is set up so that it's from 0 to infinity. You're not allowed to take the logarithm of a negative number. So you want to make sure that when you're plugging these numbers in, you're not going to end up taking the logarithm of a negative. And in that case, if it were, so let's say if this had been a negative 4 here, well, here we'd be trying to take the logarithm of, well, let's say over here, 3 times negative 4 is negative 12, minus 4 more, that's going to be a negative number that you're not going to be able to take the logarithm of. So in that case, that answer wouldn't actually work. But I will tell you that these two actually do both work, so you should be good with that. We'll do one more, and the rest I'm going to leave for you to practice on your own. If we have one more problem where we only have logarithms on one side of the equal sign, let's combine them to a single log. So in this case, this would be log base 4 of, since we're adding, it would be the product of x and x minus 12 equals 3, which means this is log base 4 of the quantity x squared minus 12x. So the logarithm is isolated. Now we can rewrite it as an exponential function. So we could say 4 cubed equals x squared minus 12x. 4 times 4 is 16, times 4 is 64. So we could say 64 equals x squared minus 12x. Solving a quadratic, I'd get it set equal to 0, x squared minus 12x minus 64. And again, this is going to factor. We could say this is x, what would that be? Minus 16. Yeah, x minus 16 times x plus 4. And therefore, we would get x equals 16 and negative 4. Again, if we were to plug these back in, here's a perfect example. If you were to plug negative 4 in here, you'd be trying to do the log base 4 of negative 4. But I know that this function When I were to graph log base 4 of x, it's going to look like this. Its domain goes from 0 to infinity. So -4 is not within the domain, so this is not a solution that's going to work back for us. So 16 should end up working here. So you could plug that in your calculator, make sure that it truly works out, but this means that 16 would be our only solution because -4 does not actually work. So I want you to continue working through these other problems, and I will post the key for you on our agenda so that you can check how you're doing.